So our next example in section 4.4 deals with the Golden Gate Bridge. It's a suspension bridge that spans the entrance to San Francisco Bay. Its 746-foot tall towers are 4,200 feet apart. The bridge is suspended from two huge cables more than 3 feet in diameter. The 90-foot wide roadway is 220 feet above the water. The cables are parabolic in shape and touch the road surface at the height of the center. Find the height of the cable at a distance of 1,000 feet from the center. This is also the height above the roadway. Okay, well, so this time they're not asking for a maximum or a minimum. What they're asking for instead is us to write the equation of the parabola so that we can then estimate, if we're 1,000 feet from the center, what the height is. So we need the equation of the parabola, and I'm going to use the vertex form because it's the friendliest for us. So f of x is equal to a times x minus a squared plus k. So let's get an intelligent picture. Think about how we want to do this. So we know that we have a parabola. And to me, it makes the most sense to put the middle of that parabola, the vertex basically, at the origin. So I'm going to go ahead and slice it this way and this way so that the vertex is at 0, 0. So that helps a lot because that's going to simplify this into ax squared. H is 0, k is 0. But now we need to figure out a. Now we know this is going to be a fairly wide parabola, but how are we going to find a? Well, we need that second point. So we have to find a second point. What we're going to use is the fact that the towers are on the ends, sitting here. We know that the road and the cables touch. They tell us that. Okay, well, these towers are 746 feet tall, and they are a total of 4,200 feet apart. Let me double check my numbers. Yes, 746-foot tall towers, 4,200 feet apart. Well, I split that distance. So doesn't that make this side of it the 2,100 feet? Same on this side. So in other words, I'm trying to find this point up here. And I know that point is at 2,100 in terms of x and 746 in terms of y. This problem does have a lot of extra fluff that's in there for informational purposes. We don't care how wide the road is. We don't care about the diameter of the two cables, and we don't care that it's 220 feet above the water. So all that is extra fluff. Okay, well, we have our second point now. We're going to plug that in. For our y value is 746. That's going to be a times our x value of 2,100 squared. Where a is equal to 746 all over 2,100 squared. I'm not going to take it to the calculator quite yet. I'm going to leave it like that. I recognize it's a little obnoxious to write, but I would prefer it to the decimals because I won't lose anything in accuracy. What we're now saying is that our equation for the parabolic span of the San Francisco Bay Bridge is 746 over 2,100 squared x squared. So again, x is the distance from the center. So if you give me how far out from the center you are, I can tell you what the height of the cable is. So again, what we graphed is the distance from the center and the height of the cable. Well, they're asking me 1,000 feet. So when x is equal to, 1,000 feet from the center, we're going to find f of 1,000. So we're just going to replace our x with 1,000. So 746 over the 2,100 squared times 1,000 squared. And then you're just going to head to the calculator. And once you do that, you should end up with 169.16 feet. So if you're 1,000 feet from the center, the cable is already 169 feet above you. No max or min on this one, but writing the equation correct. Example 4. Reads, a greeting card manufacturer can produce up to 5,000 cards per day. The profit made from the sale of these cards can be modeled by the function, and they give us the function. We don't have to write it. It's p of x, which is equal to a negative 0.4 x squared plus 2,000x minus 500, where p of x is the profit. So this is our profit. And x is the number of cards that are made and produced and sold. So produced and sold. So X is the number of cards. Part A gives us find the y-intercept and explain what it means in this context. Well, we know the y-intercept is when X is 0. We plug 0 in for all our X's. All that's left is that negative 500. So what does that mean? Well, this means that when we sell or make and produce 0 cards, the profit is a negative $500. That's no profit, that's a loss. So if you don't produce any cards, you're already $500 in the hole, which is never a good thing. Part B is asking how many cards should be sold to maximize the profit, and what is the maximum profit? So again, to analyze what's going on, let's think about what this is. It's opening down again, it's concave down, it's that negative, so we know it looks like this. So we know it definitely has a maximum. What are our axes? So we'll look at the function. So the horizontal axis is X because that's the variable on the right-hand side. So this is X, and that's the number of cards. So what's the output or the horizontal axis? Well, the output is P of X, which is our profit. So over here, we're going to have profit. Again, this is going to help you because when you go do that negative B over 2A, you get two numbers out of that. What do those two numbers mean? That's what we're trying to figure out. Here's what those two numbers mean. Okay, so we're going to go do our negative B over 2A to get the maximum. So that would be a negative 2,000 all over 2 times a negative 0.4. The negatives will again cancel out, and you should end up with 2,500. And that would be in cards, because we know that that's the output, the first output, 2,500 cards. And that answers the first question. How many cards should be sold to maximize the profit? Well, 2,500 of them. To find the actual maximum profit, we're going to take that 2,500 and plug it back in. So that would be a negative 0.4 times 2,500 squared plus 2,000 times 2,500 minus 500. Now we'll go to our calculator, plug that all in, and if you do that, you get a really huge number. So $2,499,500. So if we make and sell 2,500 cards, we will make $2 million in profit, almost $2.5 million in profit. Not bad for our manufacturing greeting card company.